Hello, friends. Welcome to part 3 of the machine learning track in the year of our Lord Global Hack Week 2022 December. So good to have you here. Hello, Fancy Appleby. Thank you for dropping that check-in link. Oh, it's the wrong check-in link? Do not trust Fancy Appleby, apparently. Deekshith, so good to see you. I remember you from last time. Nishit, hello. Welcome. Oh, that is the right one. Okay, cool. I will just double post as well for folks tuning in from other channels. But so good to have you here. Akib, good to see you again as well. Also, for what it's worth, if I call our username and I am mispronouncing something, don't be afraid to be like, actually, you should say my name this way. Because usernames are not really given to pronunciation easily. But there is the check-in link. We have a really jam-packed day today. It's going to be a good time. We are finally going to actually build our machine learning model. It's it's something that I internally struggle with every Global Hack Week is, oh, we should just jump in and just do some machine learning. And then I have to pull it back, and it's like, if we want to do anything interesting, we really have to spend at least one day of actually learning new things and preparing and playing around with our data. So that is always a struggle, but we are there and you have made it, and it's so good to have you here. And we are going to really have some fun. Oh my goodness, M. Fawad, maybe. So good to see you. I'm glad that this is the first time you're tuning in live. Hopefully you've been able to watch the other ones sort of not live, but I'm glad you're able to make it live here. So welcome. We will hang out for another few seconds. I guess housekeeping. Today we're going to build a model. Hopefully we can move fast enough that we build the model. But if I'm ever moving too fast, please let me know. Drop either a question or just a comment that says, "Hey, Will, you're moving a little bit fast." Hopefully by tomorrow we'll be able to sort of fine-tune our model and introduce some new elements to it. Tomorrow we will also announce our raffle winner. I will show up with my face painted because today we'll do our final vote of what I'm painting on my face. I can reveal what the two options are. And then I think also there are 2 new pieces of art in my home that I'm interested in showing off tomorrow if we want to do another mini art tour. Oh yeah, Fancy Appleby will be in Disney World, Disneyland, I believe, which I'm sure will be a lot of fun. But if you check in for the first 3 and do the feedback form for all 3, then you will be in the running for the raffle. I think I'm going to pick 3 people to get a swag drop. So the odds are good, given that we have, I think in the last session, 18 people submitted the feedback form. So what is that, 1 in 6? You have a 1 in 6 chance if you're submitting all 3, which is probably even greater because probably not all the people from yesterday will fill it out today. But we have a lot in store. I think we're probably going to get into it. In fact, actually, I'm going to prophylactically pop a lozenge into my throat. We're doing way better on taking care of my throat these days. I think in past Global Hack Weeks, people have noticed that after the first 2 sessions, I'm gasping for air and I just sound really raspy. So we're going to stay lozenged. Actually, here's a question. Can you, are you able to understand my voice just as well when the lozenge is in there? Because if it drastically hurts the stream performance, maybe I can pop it in afterwards. But hopefully we're good. Hello, Mo. It's good to see you. Okay, if I do that, it probably sounds worse. So, hey, it's good to see you. Although it actually is right on target because we're doing audio processing. One thing I wanted to actually test is I think I have figured out the. Oh, that's not what you're supposed to see. Never mind. Let's see. I think I figured out how I want to show off the audio. Add existing desktop. Okay, so we're just going to test to see if y'all can hear my audio, which I believe I have our notebook from yesterday up, which is actually great. We could do a little review from yesterday. Let's increase the size a little bit there. So the main things we learned about yesterday, we learned about how to use NumPy If you have never used NumPy in your life, there might be a few things that we talk about today that might be a little bit new. So we figured out how we could build these arrays and how they could have multiple dimensions and different shapes. And we were going to use arrays with lots of different shapes today. So it's a good time. And then we really got into audio, and we actually downloaded some audio samples, and we used this Librosa library to play around with our audio. And we learned about the sample rate, which is how many times the microphone is actually reading how much pressure there is in a sound wave. We plotted this so we could actually see our sound wave. And hopefully, this is the pièce de résistance. Was that audible? Let me know in the comments. Incredible. Okay, I'm going to hope that means that y'all can hear that audio. But if you couldn't hear that audio, let me know, and I will, I guess, at least try to fix it for next time. Let's see. Drop the form link. I'll drop the feedback form in a minute. I'll also drop the, if you want to look, if you didn't get this link, I will copy this. And oh no, it wasn't audible. Oh no, that's a shame. Okay, let me spend 2 seconds seeing. Let's see. The desktop audio is there. Oh, let me make sure that my microphone for audio. Okay, there it is. There it is. Let's see. If I switch to well, that's probably not what I want. Okay, that's unfortunate. Apologies for testing it out live on air. Hopefully I'm audible now. We'll give it one last. I don't know if you could hear that or not, but if you couldn't, we're just going to run with it, and I will. Oh, you can. Oh, that's great. Okay, so we can play around with audio, and you can actually hear what I'm playing. That's incredible. A couple of the very rudimentary ways that we played around with this sound data, we could just multiply our sound data numbers by 4, and that made it louder. So hopefully you could hear that, and that obviously is louder. We could also increase the sample rate. So basically just say, oh, all of this sound happened in a shorter period of time. And then I sound like a chipmunk. And then the last thing we played around with is resampling. And so our really sort of dumb version of resampling was called linear sampling. Okay, yeah, it sounds like a mess. And then the last thing that we tried was this better resampling algorithm, which was still not incredible, but it sounded a lot better than the linear resampling. So this was mostly just to get us in the mood of thinking about sound data and understanding what's actually going on under the hood. And then we also generated our own sound with pure math, right? We did some math with sine functions, and we realized that we can, if we want to, just generate with sine wave. Oh, I didn't run everything. Let's import NumPy. Apologies for the whiplash. Oh yeah, right there, import NumPy. So we could generate our own little curve, because all sound is a pressure wave in sound, or pressure wave in air going up and down and up and down. And so, oh my goodness, so many things to import. So we have one sine wave here, and then we could create a different one. And if we add them together, we get this sort of interesting compound sound. And so we were able to actually, with our little math, this is that first curve. Oh, sound file. Can we just import sound file? Sample, okay. This is one of those times I don't like clicking run all cells. But this is the time where those people that say, oh, you should just click run all cells. This is the time where they get to be like, see, I told you. Okay, we're gonna run all cells. Let's see. Runtime, run all before. So that button just is gonna run all the cells sort of above the current cell that we've selected, so you can see they're all running. I'm sure some of the imports are taking a long time. All right, our timing experiment is running. Hopefully none of this is new. Hopefully all of this is stuff that that is review if you turned into the last stream. But we'll get to the good stuff in just a second. Mostly I just think the thing that we did where we generated our own sound waves was fun. Okay, so mostly I just thought what we did last time was kind of dope, and so I want to do it again. So this is generating that first pitch. So we play this. This is literally just this curve right here turned into sound. Just kind of a pure tone, right? But then when we add it with this additional wave and we get this kind of funky looking guy, if we run that, we get something that, depending on how generous you're feeling, either sounds like a bagpipe or like a buzzer or something. And so this was where we kind of left off, where we said this idea of being able to pull the individual frequencies back out could be really useful, right? Because there's obviously this one tone and this distinct tone that might indicate different things. For example, it might indicate sort of how high-pitched or low-pitched a voice is. And so that is something we're going to touch on today, is this idea of can we, from a whole sound, sort of pull apart the individual components. Oh, okay, you're still can't hear the sound. Okay, well, that is a shame. Hopefully you can still hear me, but I will play with it again before the next session, and maybe we can get somewhere. But for the time being, I want to, not you. I want us to go and create a fresh collab. So again, that is collab.research.google.com. And we can click New Notebook just to give ourselves a fresh working space for us to actually get our hands dirty today. And let me shuffle around some windows off screen. And we should be ready to go. Okay, so I actually want to do a quick poll before we get going. I'll share the link in a second. So the question is, if I ask you, what is the definition of machine learning? I am curious, just a yes or no, do you have an answer? If I just ask you, what is the definition of machine learning? Does something pop into your head? And if you're like, no, nothing pops into my head, just be like, no, I literally don't know what you're talking about. Drop your answer in the chat. But if you do have off the top of your head, like, oh, this is what I would say, this is machine learning, drop your definition. Okay, Fancy Appleby, let's see. What is your definition of machine learning? Okay, Stuart. I'm sure Stuart has actually. I'm curious what Stuart's definition is as well, and maybe they'll just be the definition, or the definition that I'm going to use. We'll call this 2022-12 Part 3. Yeah.
Go the Techie has one, Akib has one, teaching computers how to self-learn things. Okay. I like that as a definition, I like that as especially just a description of what's going on. Bareed said general idea, but not enough to explain, and that's totally fair. I think for a lot of people, it's like, well, I kind of like, I know it when I see it, right? If you describe something to me, I can tell you if that is machine learning. Stuart said an algorithm that improves with the amount of data. Okay, this is a very, very good definition, and this is kind of the direction that I'm going to push us in. So the academic definition that we use is your computer is trying to do something, or your algorithm is trying to do something, and if it gets better at that task with the addition of more experience, which usually experience just means data, then it is doing machine learning. And so we could say, if I was going to type out a definition, which seems a little bit silly, but we could say machine learning. When your computer is trying to do something, or we could be more specific, we could say algorithm. You're trying to do something. If it gets better at that task with the addition of more experience, which in parentheses we'll just say data, because usually experience is data, then it's doing machine learning. And I like putting this out here just because it's good to get down to the bottom of what we really mean. Artificial intelligence is sort of this more broad term, and artificial intelligence just means anytime a computer kind of seems smart, right? So like you could say Clippy is artificial intelligence, but I don't necessarily think that Clippy was using any machine learning. Let's see. ML is where you make a program that takes samples to learn things by itself as part of AI. This is a pretty good definition as well. Making models that learn from data and use it to collect more data to learn more, and so on and so forth. There's kind of this idea of like a flywheel in there. On the basis, it's if your algorithm is getting better at something as it gets more experience, then it is doing machine learning. And underneath that umbrella of machine learning, we're really doing what's called supervised machine learning. And this is basically where your AI, your machine learning algorithm, is studying for a test, and you give it a study guide that has both the questions and the answers, right? So you're giving it a bunch of examples where you know the answer, and you're going to ask it to learn from those examples. Ultimately, the thing that's actually doing the learning, a lot of times we kind of throw up our hands and just say it's a big jumble of math, and that math is going to try to change itself in order to get the best at answering these questions. But we will actually, at the end, I'll throw a video in the chat on a very specific kind of big ball of math that we're going to use tomorrow. But yeah, I think a lot of folks have a general idea of it, and this is kind of the working definition that we're going to use just to ground us. So there are a lot of different ways to do machine learning, even just like a very basic stats understanding of like linear regression is machine learning. But there is one library that's really, really big for us called TensorFlow, which really helps you wrangle that big ball of math. And TensorFlow is great, but using TensorFlow by itself can be a little bit daunting, especially if you're just trying to get something done quick. And so there is a really nice library on top of TensorFlow called Keras that we'll be using a lot. And the description that I like to give is Keras is kind of like Legos for machine learning. It gives you a bunch of these building blocks, and you can stick them together in different shapes. So those are the tools that we're going to be learning today. The first thing we're going to do is actually install a fresh copy of TensorFlow and TensorFlow datasets, because we're going to use some data from that. So we'll say pip install -u, and we'll say pre-TensorFlow, and then TensorFlow, TensorFlow datasets. So this is our library and a bunch of datasets that it often comes packaged with that we're going to use. And that should take a second. Okay, I will also drop this link. So if you want to just follow along with what I'm doing in the in my Collab notebook, then you're welcome to just kind of tune in that way and check. You can also use it for copying snippets of code if you're trying to follow along, but I type a bunch of code really fast and you're like, wait, what did he just do? Feel free to copy and paste. Obviously, I think if you're trying to learn, one of the best ways to learn can be to try to do this yourself and try to break it and try to mess around with it. But copying individual commands I write down is obviously totally fine. Okay, one more thing that I want to do, and this is really more of like a best practice when you are doing science, is doing something called setting a seed. So we're going to import TensorFlow, and we'll say as TF. So remember earlier we said import NumPy as NP, and that is just sort of a standard way of importing NumPy, so you can refer to it by a really short abbreviation. This is the same thing. Oh, TF. And we'll also import NumPy as NP. So as we go about and actually are building our big balls of math that are our machine learning models, something that's going to happen frequently is there's going to be random selection of things. There are lots of different moments in this process where we're going to use a random number generator. And the tricky thing is that depending on how that random number generator works, you could end up with radically different results from me. Probably they won't be radically different, but we often have this issue of, oh, I'm running this and my model is saying I am getting 95% of the predictions correct, but your model says it's only getting 92% of the predictions correct. And sometimes that's because we generated slightly different random numbers. One place this will pop up is we're going to, when we have our big data set, it's kind of like our study guide with labeled questions. We're going to be randomly picking some of those to be our training data and some of those to be our validation data. And if you pick different samples, then you're actually going to be giving your algorithm a slightly different task. So what we're going to do is we are going to set seeds. So we can say seed equals 42. It is a common seed people like because it's the meaning of life or whatever. And we can say TF random, and we'll say set seed and pass in our seed. And then we'll also, because NumPy will also do some random generating, we'll also say NP random seed, and we'll pass in our seed. So if you didn't do any of this, the rest of the code would work just the same, but this will kind of ensure that your results should basically look like my results, which should be helpful. But if they don't, if they're just close, then I wouldn't worry about it at all. But it's generally a good practice when you're doing the science. Okay, so something that we're going to do now is pull down data, download some data to our local workspace. We did this the other day. We didn't end up using too much of the data because we were just playing around with sound. But this time we're going to import a pretty big data set. So we will say TF for TerraFlow. The context here is that I am using a piece of software called Terraform at work a lot that lets you do cloud stuff, but that also is abbreviated TF. But we will use TensorFlow .keras.utils.get file. So this is going to get a giant zip file for us that has our data set. And we are actually going to be using a small data set of speech commands. So these are keywords that are often used specifically for ambient computing devices, which we can talk about a little bit more in a second once we take a look. So we will say mini speech commands .zip, and we will have to give it the specific location, which I have copied over here, and I will just copy and paste that. So this is where on the internet it can find this data set. And then because that's a zip file right there, it's compressed. We want it to automatically extract that for us. So we can just say extract equals true, and this will automatically unpack it so it's not just a single file. Then we'll say what directory do we want it to work in. We can just say a dot means the current directory, so just the basic directory. Yeah, what happens when Terraform and TensorFlow have a baby? It's called, I guess, either TerraFlow or TensorForm. I don't know. Let's see. Cache subdir. Oh, that's not what we wanted. Oh, no. We really wanted to say data, so it'll actually put it in a subdir called data. So we're going to run that again. I don't know what just happened. It probably is messy. Oh, no, it actually looks fine. OK, so we have probably 2 copies of our data set. But we can look at our mini speech commands. And so you can see we have lots of directories here. Another way we can actually just see, because I want to keep my screen pretty clear, we can say import OS to get some functionality to look at our file system. Our dataset path should just be our current directory, and it should be mini speech commands. And if we just say OS listdir, our dataset path, not data path, dataset path, and this should list out all the things in our directory. So we have yes, stop, right, down, left, go, no, and up, and a README, which we can ignore. Let's see, can you drop the origin link in the chat? Yeah, sure, I can do that. You also can just copy it off of my notebook, but more than happy to drop it there. So this is one of those moments where if you are on Collab with me, things should work just fine for you. If you are doing something on your own local laptop, you may need to take other steps to install the things that I'm using. Okay, right on. So we've just listed the data that we have in our directory, and this is actually a bunch of additional directories. So a really common structure that we'll use specifically with TensorFlow, but I think with other libraries too, is basically if you have a bunch of examples of things. So here we have a bunch of examples of different sounds, of different utterances, or people saying things. You will put all the things that are like one another. So all the examples of someone saying yes will be in a directory called yes. Another example of this is like if we were trying to predict if a picture was of a cat or a dog, you might have a cat directory that has all your images of cats and a dog directory that has all your images of dogs. This is like a pretty common practice that comes up. And Terraform makes it super easy to interact with your data if it's structured like this. So just to make that concrete, you could have, I'll do a little comment. Your directory structure could look like data, and then you could have dogs, and then you could have image of dog 1.png and image of dog 2.png. And then you could also have cats and image of cat 1.png, image cat, image of cat, dog. I can type today, I promise. Image of cat 2, and so on and so forth. And this is basically what we have here, only instead of just cats and dogs, we actually have a bunch of different sound files. And so if we go in here, we can actually see inside down, we have a bunch of individual WAV files, which we did decide last time. We're pronouncing it WAV, not WAVE, but you can pronounce it however you want. So those are a bunch of sound files that have the word down in them, a bunch of sound files that have the word go in them, and so on and so forth. So this is our data set, and I want to spend just 2 seconds talking about why would we care about this data set, and it actually has to do with privacy. So if you are familiar, there are on stream a couple of very helpful assistants that occasionally respond to things that I say, right? And that causes me distress because it's just annoying. But there's also this concern about, is this microphone just like recording everything that I say and sending it to Sundar or to Jeff or to Tim Apple or whatever, right? And so usually what a lot of these devices will do is they will have a very small, very efficient, I'm talking enough that I'm going to make my face big for a second. They have a small version of a model that is really, really efficient that actually runs locally. And its only job is to pick up a wake word, one of those keywords that it knows that it's allowed to listen for. And this is actually why you have limited options for what you can call these things. I'm sure that one day we will have, you'll be able to name your Alexa or your Google or the other one that's on my wrist, whatever you want to name them, which would be great. But for the time being, we don't want it to listen to every little thing you say. And so it's only listening for specific wake words. And if it hears those wake words, then it will start recording and it will start streaming your audio, usually to a cloud service somewhere. People are working more with like localized models that are just doing everything locally. And I think those are really cool. And I think we'll probably get more of them. But we still have this need to have a really, really efficient, really, really solid model that can pick up a small subset of words. And so that's kind of what the inspiration for this data set, at least for me, is. That's kind of what I'm thinking about. So back to L-data. So we have looked at our data set, and now we're going to use a really handy-dandy function from technically from Keras, which turns that entire directory structure into a data set for us. So we can say tf.keras.utils, and we're going to use the function audio. Oh, there we go. It's audio data set from directory. Boom. And so in here, we're going to tell it what we want it to do to generate our data set. So the first thing we'll say is our directory. We can pass in our data set path. And this is that first overarching directory. So in our example with cats and dogs, this would be our data directory here. Then we're going to pass in something called batch size, which we can talk about in a second. Then we'll do something called validation split. And the example of why we have a validation split that I'll give is, remember, with supervised learning, it's like you're giving your algorithm a study guide that has questions and answers, right? But because you're giving it the questions and the answers, if you tested it on those same questions, you wouldn't know if the model actually learned anything or if it was just memorizing, oh, when I see these words, shoot out that answer, right? And so by separating the data set into some training data and some testing data, we can actually train it on one set of questions and answers and then test it on a set that it's never seen. So we can actually prove, does this model actually learn the underlying structure, or does it generalize? So this idea of does your model generalize, I think is one of the big challenges in machine learning, that if you are going to say, do a machine learning interview talking about the different factors that will cause your model to generalize or not generalize are probably things that will come up. So that's why we have a validation split. And so we'll actually get two different data sets that look exactly the same. Then we will pass in seed, and we can use our same seed just for consistency here. Then we're going to pick an output sequence length. So remember from last time, we looked at the length of our audio and how there's like a bunch of samples in there. And one thing that we did was downsampling, but another thing you have the option of doing is just saying we're going to cut it off at a certain number of numbers. And so here we can say output sequence. The one that I'm going to pick is 16,000. And one of the reasons that we're picking this number, if you remember from last time, our numbers ranged from like 90,000 numbers per audio sample, I think down to we generated one that was only like 20,000. And we can use just 16,000 here because all of these words are actually pretty short, which you could do by inspecting just the length of the audio files. That's what we're going to use there. And then finally, we're going to pass a parameter called subset equals both. Because we're generating with our validation split here, we're generating both training data and testing data or validation data. We want to say actually give us both of those data sets. Which means this whole thing is actually going to return two different data sets. And so we can come back here and we can say train data set and validation data set is equal to whatever this thing spits out. So let's run that and generate our data sets. Do we have any questions so far? I know we haven't like really seen much. We haven't actually gotten to look at what our data is yet. But hopefully all of this is making sense, at least at a high level. Okay, cool. So our little generate a data set utility here has given us some fun output. So it found 8,000 files belonging to 8 classes.
Sorry, I can't find any devices in your home that can
Oh my goodness.
You might want to check the device settings in the Google Home app.
Fancy Appleby has no questions, which is great. Incredible. I lost my train of thought. Okay, yeah, so if we go back up here, we see we have yes, stop, right, down, left, go, no, and up. Those are our 8 classes. And so it says we have 8,000 files belonging to 8 classes, and that's because each of them has 1,000 files underneath them. So we have 1,000 examples of each of these. And so then we see we have 6,400 for training and 1,600 for validation. And that's because we split our original 8,000 examples into a training set and a validation set. And so those are our 2 data sets. Now, just to play around and inspect things, we can check the type of our data set, the type of trained DS. It is actually a TensorFlow batch data set. So we mentioned this batch thing, which we didn't really talk about. We said our batch size is 64. And I think I'm throwing a lot of machine learning information into a short period of stream time here. So again, like shoot questions into the chat. If anything I say, even if you're like, that sentence didn't make any sense to me, I can walk back through it more slowly. But so remember, our data set is basically like a set of questions and answers, kind of like a study guide. And our batch size is basically how many questions do we want our machine learning algorithm to look at for every study session. So a study session for your algorithm is going to consist of it trying to produce answers for all of your questions, and then seeing if its answers are correct. And for every answer it gets wrong, it's going to slightly try to change itself. It's going to alter something to see if it could get that question right the next go around. So basically we're saying batch size 64, every time our model sits down for a study session, it's going to look at 64 questions and see if it gets them right. This is actually a small tip, but usually with batch size, we actually do want to pick a number that is an even power of 2 because we actually get performance benefits when things fit into memory nicely. So, it's very common that a chunk of 32 things will fit into memory nicely, or a chunk of 64 things will fit into memory nicely. And so those are those are numbers you see just pop up everywhere in computer science, but we often pick one of those. Batch size is also a great thing to fiddle around with if you're trying to alter how your model is performing. It can be a fun thing to play with. Programmers do love powers of 2. It's powerful. Teehee. Okay, let's just explore our data set a little bit more. So our trained data set actually has a property called class names. And we should be able to see this is basically a list of down, go, left, no, right, stop, up. And yes, these are the 8 different possibilities we have for classifying our audio samples. And I actually want to turn, because we're going to use this later, I actually want to turn this into an array. This is, I think, the first NumPy array that we've made today, but there will be many more. And we can call this label names. And we'll use this going forward. And we can just print this out again for posterity. Another thing that we can look at is if we pull up train DS again, so our training data set. I don't know if Polar Void is here, which is a shame because he asked for this particular stream topic. But yeah, perhaps he will pull through later. He pulled through at the end of the last session, and I'm sure he'll watch them later. But I do think it was a great idea. I'm super pumped for it. Okay, so another thing we can look at is something called the element spec. And this is basically a really complex version, or a really high information version of the shape of our data. So remember we talked about how a tensor is basically the same thing as a matrix, and that's basically the same thing as a multi-dimensional array, right? And so a tensor spec is basically a specification of what that array looks like. So here in our data set, we actually have 2 things. If you can see, this first line is the first tensor spec, and the second line is the second tensor spec. And the reason there are 2 is because it has both our audio sample and the label in there. So you can see our label is just a number, and that number is going to correspond with one of our names, or one of our label names up here. But then this first thing is our audio input. And so you can see the first thing is none, which just says we might have multiples of these samples. The second thing is the length, the number of samples we have, or the number of individual recordings of the microphone we have. So remember, we said our sequence length should be 16,000. So that's showing up here. But then this last dimension here, this is actually something for channel information, which usually, it can mean multiple different things, but it usually in audio refers to like a stereo output. So is there a left component or a right component? And you can do a lot of interesting things with channel information or with stereo information, but our data set doesn't actually have any information there. That's why it says none. And so we actually want to drop that data out. So what we're going to do is we're going to get rid of our stereo information by defining a function called squeeze. So we're going to actually create this function. So we'll call squeeze, and we will take in our audio and our labels. And all we're going to do is we're going to use terraform.squeeze on the final axis of our tensor. So we can say audio is now equal to tf.squeeze. We'll pass in audio, and we'll say the axis we want to squeeze is the last one. And so there are a lot of different ways to refer to the last thing in Python, but the easiest, simplest one is just saying -1. So whatever the last axis is, just squeeze that out of existence. And then we can just return our audio and our labels. Will hate stereo audio. Yeah, I'm not a fan of it. I think you have 2 ears, and you should have one audio source that allows you to place that audio source in space with your 2 ears. None of this stereo stuff. So we're going to not return audio, but just return audio. And we're then going to apply this function to both of our data sets. So remember, with a train set and a validation set, anything we do to one of them, we actually want to do to both of them. We want to treat our training data set and validation data set basically identically. So if we do something to our training set, we want to also do that to our validation set, which is actually the reason that we turn this into a function. So we can say our training data set is equal to train ds, and then we're going to use the map method. So if you want to do something for everything in your data set, map is really powerful. So you can basically say, apply this squeeze function to everything in the data set. And then we'll say tf data autotune, which basically just makes it so that we don't get any weird artifacts when we're getting rid of that extra channel. So it's basically telling us how we want to squeeze it out. Cool. And then the final thing we want to do here is also do this for our validation data set. And so we can do the exact same operation just on our validation. Doesn't immersive audio come from stereo? Some people will claim that stereo audio is more immersive. Yeah, I don't actually have a take here. I think we want to get rid of it because it's easy to process. Stereo audio is no shame. Awesome. So now I want to actually check the elements specification again. And boom, you'll see up here we had this third axis in our shape, and here we only have 2. So we're basically saying every element is just a collection of 16,000 things. So this is great. And I think that the time that we're spending on making sure we know what the shape of our data is time well spent. This is why we spent half of yesterday just talking about like the shapes of NumPy arrays, because making sure you know what the shape of your data is going to pay dividends time and time again. Yes, it would. I mean, you could build an algorithm that does actually take into account stereo information. We just don't have stereo information, which is why we want to get rid of sort of the empty slot. So now there's going to be something that we're going to do that's a little bit weird, and I mostly will say just trust me on it. Because your data set is what's called a Python generator, if you want to get one thing out of it, one of the cleanest ways is to write kind of a dummy for loop. So we're going to say, for example audio, example labels in trainds.take1. And all we're going to do is we can just print this out. We can say example audio.shape, and then example labels.shape. So when we run this, we get 16,000 and just 64. And what this means is that we are we are getting a whole batch of data. Remember, we earlier said that our batch is of size 64. And so this is giving us a whole set of 64 questions and answers. And these are our questions with 16,000 sort of audio samples, and then 64 total answer, or like one answer for each question, basically. So one label. Sweet. So we have some example data, and why don't we actually take a look at it? Yes, I will drop the. I'll drop the feedback form in we'll do it right at the top of the hour. We'll do it in 15 minutes. But it is coming. Yes. Okay. So we can import matplotlib as pyplot. Not as pyplot, matplotlib.pyplot as plt. I love how fancy Appleby has just taken up the summarizing stream service. This is great. This is awesome. But yes, all of the forms there, and I will pass the feedback form in like 15 minutes. Okay, so we're going to import matplotlib just to look at our sound data, just like we did yesterday. But we want to do it for multiples, so let's look at the first 4 things. So we'll say for I in range 4. And we're going to, let's give ourselves a big figure. So we can say PLT figure and then pass in a figure size. And we can say 20 by 3, so it'll be longer and not that tall. And then we'll say plt.plot, and we'll just want to pull in our example audio. We could pull in like the first thing, but because we're in a loop, we'll pull in the ith thing. And we'll say .numpy just to get a clean numpy array out of this with no other metadata. Then we can drop a label on there that will pull out label names. Actually, okay, so this is something that I want to, maybe we'll run this twice. So our example labels, just like we have example audio, we can get the number I label out of there. So we say label equals that. And then we could say PLT title, and then pass the label in there. Now, if we run this, we'll see that our labels are actually just numbers. Oh, cannot convert to eager tensor. Interesting. That was not particularly expected. But we just ask that to be turned into an int. Will that do it for us? Okay, cool. So you can see, and it might be a little bit small. I could zoom. Hopefully you can see, but there's actually our titles are just numbers. So we have, this is the sound wave for label number 5, and here's the sound wave for label number 0. And that's not super helpful. And so what we can do is we can actually use that number as an index for our label names. So we can actually say label names and just pass that in as our index. And so now, if we run this again, take away the int constructor. Now we can see right here the actual word that this is for. I'm glad to hear it's good enough. It's getting by. So this is a sound wave for, or waveform for the word stop. Here's a waveform for the word down. Here's another waveform for the word down. Here's a waveform for the word left. And those will be our sort of 4 examples. Now, this is, I feel like my sneaky plan with Global Hack Week is to always somehow bring it back to linguistics. But the world of phonetics in linguistics, I think, is super interesting. This is the idea that the sound that you are making is really a function of the shape of your mouth. So this is like, I don't know if you've heard the thing where you can't say, there are some words that you can't say with your lips touching. Or what is it that when you say touch, your lips don't touch, but when you say something else, your lips do touch. But my secret plan is to also use the swear. I think I already used a swear pass yesterday, but I don't know. The sneaky truth is I have unlimited of those. But so something that I think is fun here is to look at these sound forms and actually think about what is your mouth doing when you say stop. And you can actually kind of see it here. There's like the s is this sort of like not super loud, sort of low sort of hiss. We call it a fricative in linguistics. And then it's stop. So you have this really, really big, this is probably the t sound right there that pokes out as really concentrated. Then our vowel is really, really big. And then kind of fluttering off into a p that kind of gets lost there. Down, you can kind of almost see it here. Down, where you have the w sound kind of popping out at the end there. And you can see that these shapes are actually pretty similar. Here's actually pop quiz. We see this little, basically a sine curve popping through here. What is that? If you had to guess what that is, it's not a super specific answer. If anybody has a like what would you label this sound curve as? Yeah, exactly, Mo. I would say this is static in the background. Yeah, this would be some kind of relatively low pitch that is. I mean, because if you think about it, this is actually a really long frequency, or really, really, really low frequency. Given that we can actually just see it in this waveform. So this is some kind of background noise or static or buzzing. Probably actually not static, probably some kind of pitch because we can see that curve. And then left, I like left as well because you can see the t sound. Something that, y'all, I'm sorry, I'm kind of falling into the nerd rabbit hole here, but something that I think is really cool is, okay, this t sound is right here at the end. And if we come back up here, it actually looks pretty similar to this t sound in stop, which I just think is dope as hell. Oh, okay, there's my swear number too. So I think that's really cool that we can see those things in there. But so now we are going to do our Fourier Transform. Now, if you watched the required reading from yesterday, it wasn't actually required, nor was it reading, but it was a YouTube video that I dropped. And I'll actually drop it again in case anyone is interested, if I can find my notes. Let's see. Okay, yeah, so this was our link from yesterday on how Fourier transforms work. But it basically is, if we grab our, where is the one we were just looking at where we had two different curves and we added them together, a Fourier transform basically tries to undo that process and tell you how much there was of each frequency at any given point in time. And so that is what we're going to be building right now. We won't have to do the math ourselves. If you watch that YouTube video, the math does get, I mean, I think it's really interesting and I think they explain it really well, but the math is relatively complex. And so we're going to use a sort of ready-made solution for this. So we're going to, and when we generate this, this sort of graph of how much there were different frequencies across time, we are going to call that a spectrogram because there is a spectrum of different frequencies, and this spectrogram will show you how much those different frequencies show up. So we're going to define a new function called getSpectrogram. And this is going to accept, we'll call it a waveform. So these are, our word for these things will be waveform. Okay, so this is a sort of a great example. It's like when you take music out of a song to leave only the vocals. Yes, I think maybe the easier or a slightly easier example would be like for down right here. We know there is this background noise, and we even know that there's basically a consistent pitch. And so if we could just say, well, what pitch is that? Then we could delete that pitch out of our sound. And that would be sort of a very simple version of this. It would be the building blocks for doing something like removing all of the vocals or all of the instrumental and leaving just the voice or just the instrument. But yeah, maybe a simpler version you could wrap your head around is if we could just figure out what frequency this background noise is, we could just subtract it out of our data. So get spectrogram. And the first big step we're going to do is we're just going to use something called TFI or TF signal.stft, which stands for, I believe it stands for stable time Fourier transform. Generally, the Fourier transform will just be for your whole period and just give you back a single set of frequencies. But we actually want to see how our frequencies change over time, ergo the ST. And so we're going to pass into STFT is our waveform, which is just sort of our raw data. We're also going to include something called frame length. And this is basically, we'll pick a relatively moderate number. This is basically how many different samples does it look at once to search for frequencies. Then we'll also pick a frame step, which is basically our rolling window. First, we're going to look at all of this data. And then we're going to roll our window forward and look at all this data and get the frequencies at each of these individual steps. But again, don't worry too much about the math of the Fourier transform. Just know that it helps us sort of break down our sound curve into the individual frequencies that make it up. Okay, so then we can actually create our spectrogram. Actually, we'll grab, we'll grab spectrogram. And then, because our spectrogram actually will have what's called phase information in it, this is sort of the simple way of explaining this is that in this case right here, the curve spends a little bit of time being above the graph and then a little bit of time being below the graph. And really, we don't care if it's above the graph or below the graph. We just care that this frequency is happening. And so the way that we can do that is we can just take the absolute value of our spectrogram. Again, I would say, hopefully that gave you a little bit of intuition, but don't worry too much about the specific math here. And then finally, we are going to, we're going to add a dimension of basically of color that will just allow us to render this basically as an image to see it easily. And so we'll say spectrogram, again, overwriting it, equals spectrogram, and we'll say ... to select all of the data, and then comma tf.new axis. New axis. Again, don't worry too much about the specifics here, but this is going to let us render it as a pretty looking image, if I can spell spectrogram correctly. And then we can just return our spectrogram. Okay, so this is, because this is actually a lot is being done in this function, I'm going to add some comments for posterity. This does a Fourier Transform, pulling out the individual frequencies that make up our sound. This gets rid of the phase data, which is basically if we're in the negative or positive part of the curve. Yeah, there's a lot of typos. We're doing it live, y'all. We're doing it live. I'd like to see you type without typos on stream. I know, no shame. And just keeps the magnitude part. And then finally, this lets us render our data as a pretty image. Okay, so we have built our function to generate a spectrogram. And now, bear with me, because we're going to build one more function that allows us to actually plot our spectrogram in a pretty way. This is actually the thing that's going to create our data for us. But now we're actually going to build a plot spectrogram function. And then we're going to be able to see this data pulled apart into pieces. So we can say def plot spectrogram, and that will accept a spectrogram. First, we're actually going to check for how big it is. So we're going to say if the length of what the size of our spectrogram is, if the length of our spectrogram is greater than 2. We're just going to make sure that the shape of it is that we have 3 total dimensions. So we're going to say assert length of spectrogram dot shape is exactly equal to 3. And given that we know it is equal exactly to 3, we can say spectrogram np squeeze. That np squeeze, again, it gets rid of dimensions for us, and we're going to get rid of the last dimension again. Now, assert is, I could show maybe a very simple version of an assert. Asserts are really nice when you want to make sure that something is true in your code. So let's say that we have a name, and my name is Will, and I only want to do the rest of the code. So we'll say the rest of the code that is only for Will. So something that we could put is we could say assert name equals Will. And down here we could say print, hey Will. Kind of a silly example. So we reprint hey Will. But then if we change the name to Mo, then we get an assertion error. We say, hey, the assumption you made isn't actually true, and so I'm freaking out. That is what the assert does. And so basically it lets us ensure that something is true about our dimensionality. Mo said, actually, I was helping someone with Python the other day and had to stream my coding, and it was a complete mess. I was making like 2 typos per block of code, and I definitely ain't a bad teacher, of course. Yeah, no, I hear that. I don't know. some saying about your evident knowledge is inversely related to your distance from the whiteboard, which I feel like translates to sharing your screen as well. The closer you get to like actually showing people what's going on, the knowledge just goes out of your head. But yeah, it's tough. Okay, so we made this assert just to make sure that our data is in the shape we want. Again, this is just a utility for us to plot our graph. Or first to plot our, in fact, actually, because I don't actually care that much about this function, I actually have an example of this function working. I'm just gonna copy and paste this one because we could explain all the parts of the plotting that we're doing here, but it's not the most important part of the stream, and so I don't want to spend too much time on it because we're at halfway already, which means I will drop the feedback link. So this is our full function that I wrote up. And we should be able to run this and actually get an interesting spectrogram out. Yeah, we want to get to the actual machine learning. That's what I'm trying to do. That's what we're trying to get to. Also, because we're at halftime, let me drop the feedback form. I, of course, want to know if we're going too fast or too slow. And, of course, the all-important, what should I paint on my face? So the two options now are a Christmas tree or blahage. These are the two top vote getters from our last poll. And so whatever this says, I will paint on my face for tomorrow. I withhold the right to either do it like either over my whole face or just like on a cheek or something. But we'll see. Okay, right on. We're getting to the good stuff. So what we can do just to start visualizing our data, we can grab just one sample for our audio. So we can say current audio equals example audio, get the 0th thing. And we can also do this for labels. We can say current label equals example label, example labels. Example audio, example audio, and example labels. And so if we were to just inspect these, this is just our giant list of numbers that created that waveform. And then our label will just be a number. So this is number 5, but we could actually check what it actually is, which would be some label. But so now we can, let's say, plot a figure of size. We'll make this pretty big. Let's say 20 by 5. And then we'll actually pull out our time scale, which is just going to be a range of numbers ranging from 0 through however many audio samples we have. So if we took our audio sample, if we just take length of it, okay, it's 16,000, and so we just want a range. We can say NP range from 0 through 1600. And then we can just plot our timescale against our actual audio, which again we'll do .numpy to pull out the specific numpy array there. And then we can do the same thing for our spectrogram to compare it. So our spectrogram is just going to be equal to get spectrogram function that we wrote earlier. We'll pass in current audio. We'll also create a new figure that'll just sit side by side, and we can call plot spectrogram. If we run this, if we did everything right, boom! Okay, we've got some fun data. This is good. This is great. So we have the same time axis, right? We have throughout here, things right over here are sort of related to the same part in time. And then here, they're related to the same part of time at the end. You can see it tapers off. And so already you should see a little bit of, like this should make a little bit of intuitive sense, right? Like just the loudest part, we have the brightest values in the middle here. We also have some audio over here. And this was, I believe this was stop, because we have the S sound and the T and the big O vowel sound. But we can get even further. So you can see our S audio here is actually a pretty high frequency. And you can even think about that. You can actually make the noise yourself and say S, and it's kind of a higher pitch, right? Our t sound actually kind of covers the entire frequency range, and plosives, which is a t or a p or a k, are all called plosives, and those often will give you a wide range of frequencies. And then our vowel is pretty actually low in our frequency range. The O is pretty good, bit low, and then you can even see our p right over here, another plosive that kind of takes up our whole frequency range. So this is kind of diving deep into a spectrogram, but the important thing is this is a really, really easy way for your model to look at your data. This is something that we think about a lot is there any easy math that we can do? Well, not easy math, but is there any math that it's easy for a computer to do that it would be hard for a machine learning algorithm to sort of reinvent, right? And we know that the frequencies are going to be important, and we actually have an easy math tool to generate that for our model. And so this is going to be a much more useful data input for when we're actually training our model. I appreciate that you think it's epic, Mo, because I also think it's kind of cool. Fancy Appleby, since you're probably painting a Blahaj on your face, are you a proud Blahaj owner? Okay, I wouldn't be too certain. There are people who aren't part of Blahaj gang here. A lot of people are feeling the Christmas spirit. Let's actually, now I'm actually kind of curious to take a break and see where the poll is at. Okay, we only have 4 responses so far, and it is a dead tie. It is 2 votes for Blahaj, 2 votes for Christmas tree. But to not answer on your question, I still don't own a Blahaj. The last time I went to IKEA, they were sold out. I did think about getting it though. Most of it's at the end, which actually I appreciate, because then you can rate the entire stream as a whole, which is, I suppose, maximum information preserving for me. So thank you very much. Right on. So we have generated a spectrogram, and we've gotten to look at it, and we've gotten to actually dive into what these individual parts mean. Does anybody have questions about what this spectrogram means? We have time on one axis, and we have frequency on the other axis, and then the color represents how loud is that frequency. And we even walked through the example of the word stop, and kind of piece by piece realized that, oh, sa has this particular shape, and has this different shape, and ta and pa have unique shapes as well. And this is going to be a really, really convenient way for our model to get this data. You're always trying to do as much work for your model as you can possibly do. Let's see, what does yellow in the second graph mean? This is a great question, and the answer is volume. So basically volume or how loud it is. So you can see basically almost at all times you're getting some volume of all frequencies. Some frequencies are just louder than others, right? So right here, what this means up in the bottom or in the top right, okay, I'm going to drop that. In the top left, this just means that those higher frequencies are louder. So in a sound, there probably are a few lower frequencies creeping in. They're just a lot quieter, and that's why they have sort of a darker color. Again, here with the sound, there probably are some higher frequencies, but on average tends to favor those lower frequencies. Let's see, Unacademy G fan said, when can we expect swag drop? Excuse me. Yeah, so we're doing folks who submit all 3 of the feedback forms by tomorrow. I will raffle off 3 swag drops and announce that on stream tomorrow. So fill out all the feedback forms and show up tomorrow. But if you're not there tomorrow, but you did fill out the first 3 ones, you'll still be eligible. So that is what the yellow means. No questions, sir. I'm somehow understanding this. We love to hear it. But any other questions, please let me know. Right on. Okay, so we are now going to do, let's actually look at the shape of our spectrogram. And you should, let's look at the shape of our spectrogram. So if we just take spectrogram, and say shape, we have a tensor of 129 by 100 or 124 by 129 by 1. So we only have a single spectrogram here, right? And we have two different axes. One of them is 129 is the number of different frequencies that we have. What the actual spread is, I'm not sure, but these are they low frequencies or high frequencies, is this 129. And then 124, as you can see, even though we've plotted this against basically a bunch of different samples, we have actually batched it together and looked at windows, right? So this was actually up here when we generated our spectrogram. We picked a frame length, and that frame length means that each frame is actually a pretty big chunk of data. So that's why we only have 124 sort of horizontal buckets. But so this is the shape of our spectrogram, and this is the thing that we're going to be feeding into our algorithm. So I think now really the last big thing to do before we actually mess around and build a model is to apply our get spectrogram function to all of our samples. So we could define a new function called make spectrogram dataset that will accept a whole dataset. One of the reasons that we're writing so many functions is because we want to be able to reuse them on both our training dataset and our validation dataset. Because remember, anything that we do to our training set, we also want to do to our validation set. And so what we'll do, it'll be a pretty simple command, but we'll say whatever our dataset is, map, and we're going to map, the map function we want to map onto it is actually going to be a lambda. If you're not familiar with lambdas, they're basically just a way of, in this case, wrapping a function in additional logic in line. So we'll say lambda, and then accept both the audio and the label, because our data set, remember, has both the audio input and the labels in there. And then we'll do a colon. And now we'll be able to actually just run whatever function we want here to return our new data set. So we can say get spectrogram, which remember will just turn our audio into a spectrogram. So it'll go from this will be our input, and this will be our output. And then our label will still just be our label. And then the final thing that we'll do is num parallel calls, because we want to run this as fast as we can. And we'll say tf data autotune. So all this means is that we're saying TensorFlow, as you're trying to run all this in parallel, just figure out what you think will be the best. Oh, unmatched. Do we need an extra closing? Here we go. And actually, we just want to return this. So this will be we'll just return this new mapped data set. If this lambda business doesn't make sense to you, don't worry. It's just basically our way of applying get spectrogram to our entire data set. And so now, remember, we currently have a train DS and a val DS. And these currently hold waveforms. All of these are basically sets of these waveforms. And we want to apply make spec DS to get a bunch of these more interesting spectrograms. So we are going to run make DS on both of them. So we can say make spec DS and pass in our training data set. And this will now be, we'll call it train spec DS. And then down here, val spec DS will be equal to make spec DS, where we pass in our val data set. So things are getting a little bit complex here. So if you have any questions, let me know. We can talk about it. But we are just turning our entire data sets here from waveforms into spectrograms. And the answer being, something that hopefully was evident when we talked about it was that this is actually just easier to piece apart what the sound looks like or what the sound sounds like compared to this. You can kind of squint and you can kind of figure it out if you know this is already the word stop. But this is a little bit easier to. If you were in the habit of it, you would just know what this meant a little bit easier. Right on. So we're 8:15. I think we're just gonna jump in and actually make the model now. I think we're gonna get to it. We could do more playing around and looking at our data, but I am interested in actually getting a model on paper. So we're gonna import two more libraries. We're gonna say from TensorFlow.keras import layers. So remember earlier I said that keras is kind of like Legos for machine learning, and layers are basically the Legos that we're going to play with. You can think about, we said that our in between our questions and our answers is a big ball of math, but really it's a stack of math. And so we're going to stack up a bunch of layers of different math operations to do to our input data to arrive at our output data. And then finally, we can say from TensorFlow TensorFlow.keras import models. And we're going to define a few things here. Yeah, I said model. I said the magic word. We are building a model. One thing we're going to define, because keeping track of our shapes is really important, is we're going to say input shape, and we're going to say example spectrogram. We have an example spectrogram, right? Did we never get an example spectrogram? Or we just called our example spectrogram, didn't we? And we will just get our spectrogram dot shape. Yeah, we have arrived, friends. It took us an hour and 17 minutes, but we're finally there. So let's actually print out this input shape just so we can see what it is. Because we want to actually be able to tell our model, this is the shape of data you can expect to come into you. And then num labels, we'll say is equal to the length of our individual commands, because this is basically the shape of data going in, and this will essentially be the shape of data going out. There, run that. Oh, commands is not defined. Or do we call it label names? Label names. We can print that as well. Output shape. Sweet. So we're going to get in something that's a 124 by 129, it's basically a grid of information, and we're going to be outputting 8 different values, which is the probability that it is each of our individual words that we're trying to predict. So now we're going to do one prep step before we actually literally define the model, but we're already building part of the model here, which is a normalization layer. So basically what this is going to do for us, remember that these bright colors were basically the volume of how loud these different sounds were. Well, we want basically our model is going to perform better if everything is around the same volume. And so normalization will say, take the loudest thing and take the quietest thing and try to make them all about the same volume. So we can say norm layer, this is one of the first layers we're going to build, is equal to layers.normalization. This is what I'm talking about is the Legoization of machine learning. Is there's just a normalization Lego that you can pull out. And what we have to do, because it needs to know what the full scale of volume is, like how loud is the loudest thing and how quiet is the quietest thing, we actually need to adapt that layer to the data that we currently have. So we can say norm layer dot adapt, and we'll pass in data, and we can pass in our data set, our train spectrogram data set, and we're actually going to map on it just a way of pulling out the audio itself. Honestly, I think the fastest way to do this will be we'll just say map func equals lambda spec and label. So it's going to get both the actual spectrogram and the label, and we'll just return the spectrogram. But so this ends with us just giving it basically a full list of all of our spectrograms that it can tune out the super loud, or it can normalize the super loud things and the super quiet things. You pulled out the normalization card. Yeah, it's an important step in the machine learning journey. Oh, 404 now found 19. Welcome, welcome. It's good to see you again. It's been a minute. I'm currently on the hands dirty Collab. That is true. Okay, so we've built our first layer for normalization. That is functionally what it's going to do is just make all of our spectrograms the same general volume. So now, the moment you've all been waiting for, we're going to build our Lego tower of different parts of our ball of math that produces predictions for us. And this, I think I'm going to have us build a pretty simple model today, and then we're going to ramp it up with additional power tomorrow. So our simple model, we can call this simple model. We're going to use that models directory module, and we're going to pull out the sequential object. And this basically just says we have a bunch of Legos, and we're just going to stack them one on top of each other, and it's a sequence that our data is going to travel through until it produces a prediction. And so what we're going to give it is just a list of layers. We have a list that we're passing it. And now we're just going to give it all of our layers. And the first layer we're going to give it, at each step, we're going to tell it how big the data should be at this particular slice in our model. So our first layer will be an input layer. And here, the shape we're going to give it is just our input shape. And whatever this input shape is, that's going to be what feeds into the next layer. But the next layer, we're actually going to resize it to a square. And that will actually, today we're not going to do any resizing. Today we're just going to do a simple function called flattening. So our input shape is this two-dimensional grid of 124 by 129, and then there's a single number in there, which is the volume. But we're going to flatten it just so we get one long list of all of our data. And so flatten, the one thing that flatten promises you is that it will always return a tensor that is just one dimension that's super long. Now we're going to do something called a dense layer. And someday we're going to do a global hack week where all we do is we manually implement a dense neural network together. I think it's going to be a good time. But today we could just use Carrots' math for us. But dense basically just means that you have a brain where all the neurons are connected to all the other neurons. And so every single part of our spectrogram coming in is going to be able to talk to every other single part. And this means, for example, if we scroll back up here, that if there is something specific about this frequency in the top left-hand corner that really has an important bearing on this frequency in the bottom right-hand corner, then it can do that. It could actually, those two parts of our input could talk if we wanted them to. So that's what a dense layer does. And the 128 means that its output will be the size of 128. Yes, yeah, again, powers of 2, we love them. They pop up everywhere. And now we're going to add one final layer. And we're going to say layers.dense. Now, pop quiz, what do I have to say would be the output size of this? If this is the last dense layer, what should I tell it should be the size of its output? Do we have any guesses? 20 seconds on the clock. Not actually 20 seconds. I'm just going to say it in a second. But I want to give everybody a second to drop a comment in if you want to guess what has to be in this dense layers output. Okay, so we have some good guesses. 64 is just always a good guess because it's a great number. Stuart guessed 1, and the answer is, fittingly, between the two, the answer is whatever our number of classes is. So remember we said our output shape is 8, and that's because there are 8 different potential labels that it could predict. So generally speaking, when you have a final dense output layer in a model, you want the output shape to be however many different things you're trying to predict between. If you have a multi-class prediction problem, then it's going to be the number of classes you have. So in this case, we could just say 8, but because we're good programmers, we can put num labels in here. So our model knows, oh, there are 8 different things that I'm predicting between, And so I'm going to predict a different probability for each of those 8 things. I'll give you a probability that the output is stop. I'll give you a probability that the output is go. I'll give you a probability the output is up. I'll give you a probability, so on and so forth, for all 8 of our potential words. Great, so we have built our first simple model. We're also going to compile it. So we will say simplemodel.compile. And this is where you give it a little bit more information about how we've kind of waved our hands away at this, but when it studies, how should it change itself when it gets a question wrong or when it gets a question right. And again, this is another big bundle of math that we plop in there that we could talk about more if we have specific questions. But we have something called the optimizer, which honestly, we just so very often use the same optimizer. We use the Carrots Atom optimizer, which there are great papers written about, some of which I will hope to read at some point. But this is just a very efficient way of producing the math of if you get a question wrong, how should you change your decision-making process? And then we have something called loss. So I'm going to actually write this out, and then we can talk about it in a second. So we have tf.carrots.losses, sparse categorical cross entropy. Got it. There we go. Got it complete. And we'll say from logits equals true. And then we'll say metrics will be accuracy. Okay, so hopefully accuracy makes a lot of sense to you. It should be relatively simple. Accuracy is just on the test that you take, how many questions did you get right? I give you a study guide of 100 questions, and if you get 90 of them right, your accuracy is 90%. That's cool. But loss is a little bit different. So one downside to accuracy as a metric is that it's impossible for us to give you partial credit if you kind of got almost there. Or if you said, I think it's this question, but I'm not sure, and this other answer sounds pretty good, that we would like to reward you for actually almost knowing the right answer, but accuracy doesn't do that. Accuracy just says, well, did you say, is it this answer, or did you pick the right answer? And what loss allows us to do is it allows us to be a little bit more nuanced and say, well, if you said it was A, but you said you weren't certain and you thought it might also be C, and the right answer was C, we'll give you kind of partial credit for that. Obviously, the math is a lot deeper here, but that is the way that I think about it. Oh, polar void, welcome, welcome. We were talking about it. You were like, I wonder when polar void will show up. But no worries about sleeping in. I'm glad that we got you before the end, and you can vote to see if I'm going to have a blahage or a Christmas tree on my face. I will admit, the Christmas tree will probably be easier to paint, but the blahage would be interesting. If we tie, I'll do a Christmas tree on this cheek and a blahage on this cheek. Fancy Al will be always pulling in clutch. Somebody will have to be on deputized to do link duty when Fancy Appleby is at Disneyland. No, unfortunately, actually, the Great Wave was the number 3 vote getter in the last one, but now for the final vote, we're just going to do the top 2. I think that Christmas Tree got 5 votes and the Great Wave got 4 votes. So unfortunate. Well, yeah, if you tie it, we'll get all cheeked up, as they say. That's not what that means. Okay, do we have any questions about loss versus accuracy? Hopefully that feels roughly understandable. Because now we're just going to get in there and we're going to actually run it. And this is a pretty small model, and so it'll take a minute to run, but it won't take all day. Now we're going to pick a number for epochs. And I think we're going to pick 10. We'll say simple model dot fit. So now we're actually this is basically where we tell our model, hey, we built you, we told you what you are, and now we want you to do a study session. We want you to actually take all of the links or take all the data we have and go into a room and study up and see how smart you can get. So we'll give it its study guide, which is our training data set. And then we'll give it the validation data as well, so it can basically regularly test itself to see how much it has learned. So we'll say validation data is equal to val spectrogram ds. We'll say epochs equals, let's say 10. And this is basically, remember we said our batch is basically splitting the study guide up into individual study sessions. Well, an epic is basically how many times do you go through all the questions you have in your question bank. And so we're saying go through all of the questions you have in your question bank 10 times. And then actually, why don't we get fancy and we'll do some callbacks. We'll do an early stopping callback. So a callback is basically any amount of logic you can have your model check or your training session check in between every batch that it runs. So we can say tf keras callbacks dot early stopping, and we will say verbose equals 1, and we'll say patience equals 3. So basically what this means is that if our model ever starts doing worse, and if it in fact does worse for three times in a row, then it'll say, hey, I think I've studied too much and I'm gonna stop studying now. So we're saying ideally go through the whole study packet 10 times, but if the model ever gets to a point where it starts doing worse on its tests, it'll stop and tell us. And then finally, this is going to output a history that we can graph later. So let's grab that history. And, oh, not train spectrogram, just train spec, wasn't it? And this is the moment of truth where we actually see if all of our shapes are cooperative. And given that it's actually running, it sounds like we got all of our shapes right. So you should appreciate that all the time we spent thinking about the shape of our data was not wasted, and we are actually getting our model to actually train now, which is very exciting. So a couple things that we'll pull out. Right now, it's in its training phase of this epic. And so it gives you a loss, which is that thing it can get partial credit for, and then an accuracy where it can't get partial credit. But then validation happens at the end. And this just concerns itself with questions it doesn't know the answers to already. And you can see that it's doing worse on that section than it is on the questions that it already knows the answer to, right? So on the study guide where it already saw the answers, it's getting a 60% already. But for the questions that it hasn't seen the answers to yet, it's only getting a 49% over here. And you can see now on this third round, it got better on testing itself on questions it had already seen. But it actually got worse. It went down from a 49% down to a 47%. But we're making progress in general. Another really, really important thing to call out is, okay, 63% accuracy on a test that's true and false is, a 49% accuracy on a test that's true or false is actually terrible, because on a true or false test, you should by default just get 50% if you guess. On a test that is like A, B, C, or D, if you were just randomly guessing, you'd expect to get 25%. So that actually is much better. But in this case, because there are 8 different possible labels, really it's like a test where every question has 8 different answers. And if you want to actually do the math on what would you get randomly guessing, it would be 1 divided by 8, which is basically 12.5%. So really, any amount we do better than 12.5% is actually something that our machine learning algorithm is actually able to do, right? It's something impressive. So you can see we're playing around here. This is actually an important example case of why we set patience to 3. Because if we set patience to 1, we basically say any time that you start doing worse on validation, bail out and stop training. But in this case, it actually did do worse on this one step right here, but then it kept trying and it kept studying and it crept up again. And so now it seems to be kind of leveling off, even though it keeps doing better on the regular accuracy on those questions that it already knows the answers to. On validation accuracy, seems to be slowly creeping up, but basically leveling off. And we can see on Epic 9, we got to early stopping because we were not making sufficient progress. I believe it is actually based on the validation loss here. And so you can see that we did in fact level off there. Yeah, our algorithm is definitely better than guessing. So I think that is where I'm going to leave us on the model work. When we come back tomorrow, we're going to introduce convolutions to our model. And this is actually a great time for me to leave the required reading that is neither reading nor required. But I actually have 2 links for you now. I'll drop this link. This is a computer file video on what convolutions are. specifically on convolutional neural networks. And this is going to be, remember earlier when I mentioned that a dense network is going to say that something up in the top left corner has bearing on what's in the bottom right corner down here, and that everything is connected? Oh yeah, actually, sorry, I also have the 3 blue 1 brown video actually in the notes, which I'll drop as well. This is also a good video if you want more content on convolutions. But so our dense network is basically saying all of this stuff can affect everything else. It's a brain where all the neurons are connected. But that's not how our brains work. And it actually is a little bit silly if we think about it, right? Because really we know that all of this stuff all together, like this one moment in time, it actually really, really matters. We already pointed out that there are some localized, you can actually see this is kind of the S shape right here. And we have the T plosive shape right here. And we have the big, deep O sound, that vowel in the middle there. And at the very end, we have the P plosive as well. And so there are actually localized things where all the individual parts that are close actually kind of matter. And so that's what convolutions are going to give us when we talk about them and add them to our model tomorrow. So tomorrow we're going to one, add some convolutions to try to improve our performance. We're going to look at a confusion matrix to see specifically what are we getting wrong. We are, of course, going to do the raffle, announce who wins a swag drop, so be sure to fill out my little feedback form. We're also going to see what I end up walking in painted on my face. Maybe it is a blahage, maybe it is a Christmas tree, maybe it is one on each cheek. And and if people want, I don't want to push this on anyone, but if people want, I have 2 new pieces of art that I can show off if we want to do another little mini art tour. And I think that'll be it. Do we have any questions? Yes, Mo, you can submit the form now. I'm not going to do any further instruction. We'll just be answering questions if there are any. Polar Void said it's conspiracy theorist brain. Yes, that is actually a great, I'm definitely going to steal that. That is a great explanation of what a dense neural network does for you here. It's going to put it up on the board and try to draw those connections from anything to anything. That actually is a really, really good analogy. And so that is what we're going to try to overcome. We're going to try to overcome conspiracy theory brain. Polar Void said next Global Hack Week, make some coffee art. Yeah, maybe we'll do, if we do the coffee session again, we'll do something fun. And Fancy Appleby said, I want to hear the bird song. You know, Fancy Appleby, you are part of the core Global Hack Week squad. And so if you request, then I live to serve. So we'll do the bird song today so that Fancy Appleby can experience it live. So this is, I know 2 songs. One of them is the Avatar song on the kalimba, and the other one is a song that I wrote about the truth about birds. And I think I'll play us out on that, and then we will meet back here tomorrow. All right, we got to get into my, actually, it was a great segue from the conspiracy theorist brain comment. I am so unsure about so many different things that I have heard, but there's one thing of which I am certain, that the US government invented birds. They are fake, you can see it in their eyes. They're the NSA's favorite little spies. But there's one thing of which I am certain, that the US government invented birds. Stay woke, sheeple. All right, thank you so much for being here. I will see you all tomorrow, except for Fancy Appleby. I'll see you next Global Hack Week. And thank you so much for tuning in, and happy hacking and all of that. I'll stick around for a second and respond to comments. Bye, y'all.